So obviously we've been talking about galvanic cells, and we talked about how to calculate the cell voltage. Again, we could take our cathode minus our anode. Once again, as we talked about a number of times up to this point, if you are subtracting, you again should not change the sign that you find in the SRP table for the anode, because again, that's what the subtraction is there for. Once again, if you do want to change the sign for the anode, as we talked about, then you should actually add the value after you change the sign. So you do that. We also talked about relationship between E of the cell and our friend free energy. Uh, Free energy is equal to minus NFE of the cell. Again, this is our cathode minus anode. F is Faraday's constant, 96,500 joules per volt per mole. N is the number of moles of electrons. And obviously that is our delta G, which as we talked about should agree. Again, that is why when we get a positive cell voltage, that's a good thing because that will give us a negative delta G and the reaction should be spontaneous. And vice versa, if we shoot there a negative cell voltage, that will turn our delta G into a positive and it will be a non-spontaneous process. We also related this to equilibrium constant as well, a little RT NF natural log of K. And obviously, these are our same third things. That's our temperature in Kelvin. That's our Faraday's constant. That's our moles of electron. This is our gas constant, which again is the one with energy, the 8.314. And obviously our E of our cells, our cathode minus our anode in this case. Obviously that's our equilibrium constant. And again, this is our relationship between E of the cell and K. And again, all three of those sort of values, as we talked about, should really agree with each other. So again, if you have a positive cell voltage, that should give you a spontaneous process and a negative delta G. And that all should mean that you should be heading probably towards the product side in that reaction. And because of that, you probably will have more products than reactants, and you should be looking probably at a larger value of K and vice versa. If you had a negative value for E of the cell or cell voltage, that's going to give you a positive delta G, which means the reaction is going to be non-spontaneous. That's going to mean that not too much is going to the product side. Most is going to stay on the reactant side. And when we do our equilibrium constant, again, we should end up with a more smaller value of K. We also talked about non-standard conditions, which is known as the Nernst equation. That's E of the cell is equal to E not of the cell minus RT NF natural log of Q. And remember, this is sort of like non-standard conditions. This is sort of our standard conditions. And obviously everything here is the same as before. And Q is our reaction quotient, which again is the same as we do K. So basically concentration of our products over our reactants. This is a situation where, again, we would use in a non-standard condition. And basically what that means is either your molarities or your concentrations are not 1 molar, or excuse me, if you're dealing with pressures, they are not 1 atmosphere. So again, those are basically your sort of standard conditions. So again, if you come across a problem with something that's not 1 molar or 1 atmosphere, that probably should point you to the Nernst equation. Is that's what you want to use it. Again, if it's standard conditions, then obviously you could use this cathode minus anode. Any questions on any of that stuff there? All right. So I think where we left off was we did this one, so we didn't leave off there. All right, next we're going to talk about is batteries, and you're not going to be responsible for any specific sort of battery equations or anything like that. So basically, you just got to kind of know the little difference between how a battery and a traditional galvanic cell is, and maybe some similarities as well. So, batteries are galvanic cells or a series of galvanic cells used to direct electrical current at a constant voltage. One of the main sort of differences in, say, a traditional galvanic cell and a battery is obviously it's all self-contained there in one little sort of compartment. Um, there's also no traditional salt bridge like we use in a traditional galvanic cell to sort of connect one side to the next. Similarities is they're both redox reactions. They both basically have an anode and a cathode. Electrons go out through the wire and do some type of work, right? which again is why in your battery compartment, when you look at it, there's little wires right where you put your batteries in. And again, they use those sort of electrons to do some type of work. There's different types of batteries here. This here is a dry cell. I'm gonna go with Duracell. Looks like the copper top battery there, hypothetically speaking. We have an anode, which is the zinc can or container that's in contact with this sort of pasty electrolyte sort of solution that's going to act sort of like a salt bridge to kind of keep everything flowing correctly. There's a cathode, which is the carbon in the middle. And obviously, we have our positive side of our battery and our negative side of our battery as well. This type of battery here again is going to get us a constant voltage here of 1.5 volts, regardless of the size of the battery. If it's a double A, triple A, a C, a D, whatever it may be, they all give the same voltage. Just they're bigger so they can last longer if necessary. But what we see here, if we take a looky, we got our zinc just going from 0 to +2, again getting oxidized, which is our anode part of it. Over here on the Mn side, we got a -2, that's a +4. And over here, that's a -2, -6, +3. So again, getting a little reduced as we kind of go through it on that side. It's sort of where our reduction is going to take place. Another type of battery is a mercury battery. And again, it's a similar sort of idea. It's used a lot in medicine, electronic devices. Um, it is a zinc anode that's in contact with mercury. And it also has a very strongly alkaline electrolyte. Alkaline means basic. Yes. And that would be where we have our KOH, which is obviously a strong base in this case. Again, sort of the battery acidish part of the middle part there is kind of serving as a nice little salt bridge medium to keep all the sort of charged things moving properly. We also have our cathode here, which is our steel. And there's no change in electrolyte composition during operation, and that's really good because, again, you get no degradation here of the inside part there that keeps everything flowing, so it allows it to kind of last for a very long time. Here, get a little less of a voltage, 1.35. And again, here's our zinc going kind of from 0 to +2. Our mercury over here going from +2 to 0 in this case, again, getting reduced. One of the things for long life here is also in the overall reaction. A lot of things that are solids are really good for sort of long life and also rechargeability as well. So that's usually a fairly good sign for things to sort of last a really long time. Classic lead storage battery in our cars are 6 identical sort of cells joined together. Each one gives about 2 volts, which is your 12-volt battery, which is enough to get your car started there. Ignition circuit, electrical system, unless you're late for wherever you're going, and then it won't start. But usually it's enough to turn it over. We also, it is rechargeable, right? So if you ever had to jump your car, right, they usually tell you just let it run for a while there to hopefully recharge it. We also have a lot of times in cars, alternators and stuff like that. So we do not just deplete the battery. Um, Here's sort of a cross section of a car battery, a traditional car battery. We have our anode and our cathode, right? And that's always like, which color did I hook up to jump this thing? One of those should be right. Um, Hope for the best. Cross your fingers when it's all said and done. A lot of cars nowadays, batteries are not even in the engine. They put them in all weird places, trunks and behind back seats and stuff like that. But it usually runs like a cable, so in case you do need to jump it, they usually put something like there in their engine compartment as well. They're usually sealed, so you got your something like sulfuric acid, again, a very strong electrolyte serving to kind of keep everything flowing and moving around. And here we see our lead going from 0 to +2. And on this side here, excuse me, we got our +4 for our lead there and our +2 on that side. Again, you see a lot of solid products here, which is good for long lasting for those batteries. Another type of battery is a solid state lithium battery. Again, we have an anode that's some type of carbon type of material, graphite. It also has the holes in there to allow, as this guy gets oxidized, to sort of travel across that medium to the other side. Because of this, there's not a lot of change in sort of the composition of things. These things can be recharged a lot, right? Which is why a lot of things run on lithium batteries or have run on lithium batteries, including drills and phones and all those types of things. Also, very light metal as well, so you don't get a lot of extra weight there from your battery. Now, a fuel cell is not a technically traditional sort of battery, but it sort of functions similar. And this is a hydrogen fuel cell here. And in this particular case, we get a continuous supply of oxygen and hydrogen, which is years ago what they wanted to build cars to run on is a hydrogen fuel cell and hydrogen. And the reason for that is the overall reaction would just produce water, which is kind of nice and clean. Um, but obviously, we are not necessarily a hydrogen sort of economy, and it's a little bit different than filling up gas and stuff like that. The moved away from this obviously to more obviously hybrids and then obviously full electric type cars. But the overall reaction happened here again, zero for the hydrogen, +1 on this side. So again, getting oxidized. 0 to -2, again, getting reduced in this case. And again, you would need sort of a constant supply of each of those things to kind of keep it going. Questions on batteries. Again, you're not responsible for any specific equations or anything like that. Very simple question of explain some similarities and differences between galvanic cell and a battery. Maybe it'll be question 6, question 7, 7 or 6, you choose. Let me know. All right, next we're going to talk about is corrosion. So corrosion is returning metals to their natural state, and a lot of steel production is for metals that have gone through and rusted. All metals that have an SRP value less positive oxygen gas is basically susceptible to going through oxidation. The reason for that is if you have your oxygen and you have your metal, and the SRP value for oxygen is more positive than it is for your metal. That means when you hook up basically a galvanic cell with the air in the around the room, it is going to be the oxygen that's going to be your cathode. It's going to be the sad metal that's going to go through oxidation and perhaps not be in a good shape afterwards. So when they get hooked up in that situation, based on that, oxidation is going to occur at the metal, and that's basically what corrosion is the oxidation of those metals. Now, not all oxidation or corrosion of metals are necessarily a bad thing. Sometimes they can create a layer as they go through oxidation. So sometimes you can have a metal that starts to go through corrosion. And the result of that is it makes this sort of layer of corrosion and a protective layer, and it kind of protects the metal that's underneath it from further corrosion. So although the surface gets a little messed up, it actually does sort of protect the rest of the metal from further corrosion that occurs. Aluminum is an example of that. It forms this sort of aluminum oxide layer that does sort of protect other metals or the rest of the metal from further corrosion. Problem though is, for example, with iron, it does the same thing, but that protective layer is not so protected because it just falls off. And when it falls off, it exposes new metal to obviously further oxidation. If you ever had anything that's rusted, right? People always say I could just like put my finger through it, right? And it just falls apart basically. And that's the problem with that. Obviously, when it creates that layer of oxidation, falls off, exposes new metal, and it continues to corrode until you can put your finger through, a piece of metal or something like that. Some oxidation and corrosion is expensive, right? So the greening of copper, right, is that patina color that some people really like. Silver tarnishing is silver sulfide. Gold that has an SRP value of 1.5 is actually a more positive value than oxygen. So what happens with gold, it does not go through very much corrosion at all because when you hook up gold and oxygen, it's actually gold that's more positive than the oxygen. And in that situation, gold becomes the cathode and oxygen becomes the anode. So thus, gold does not go through very much corrosion or oxidation because of that. In terms of rust, rust is actually a process where iron sort of gets oxidized twice. It starts with iron that goes to iron 2. And really, for rust to form, you pretty much only need three things. You need a little bit of iron, a little bit of moisture, and some oxygen. And on steel, there's a lot of these uneven surfaces where moisture can sit, and since oxygen's in the air, you have your three components really needed for rust to occur very easily with each other. The iron 2 then goes through further oxidation and actually becomes iron 3 oxide, which is rust. And again, problem with that is it continues to sort of fall off, and again exposing more and more metal to that oxidation and corrosion, and obviously costing money in the process of doing so. Now, there are a couple ways that you could prevent corrosion, which would obviously be the second part of question 6 or 7, which is how would you prevent corrosion? And you could apply some type of coating to it, so something like paint, the good old Rust-Oleum paint, right? So you paint something with some Rust-Oleum paint. Hopefully, it protects it. You can also do some type of metal plating to it. Chromium tin is used to plate steel because they form these kind of protective coating. You can also do some type of galvanizing with zinc. And the idea there is when you put together zinc and iron together by doing so, when we look at the two SRP values for that, we do see that the zinc is going to actually be um, less positive than the iron, and it's going to go through oxidation rather than the iron. So again, it's acting sort of as a sacrificial sort of coating where all the oxidation occurs on the zinc, again protecting sort of the iron and the main part of your structure. Alloying as well is another way. You could add some other sort of elements in, and it also sort of changes sometimes the SRP value to something like gold and that kind of noble metals, which again will allow it to resist oxidation. Another way that we can sort of protect things is through cathodic protection. And for example, if you take like a tank or something like that and you bury it under the ground, there's a lot of moisture in there. And that tank is not going to survive very long, especially if you go through sort of oxidation and start to rust out. One way you could do that is you could attach something like magnesium, and magnesium is a much better reducing agent than iron. Remember that things that are reducing agents are things that get oxidized, right? So if it's a better reducing agent, it's going to be oxidized much better than iron. So here, what's going to happen is sort of another sacrificial type of deal. All the bad oxidation is going to occur over there at the magnesium, going to leave sort of your buried tank alone there. So it does not go through a significant amount of oxidation. So you're not digging it out of the ground every 2 weeks or so because it started to rust through. And that's the idea behind this. Again, all the oxidation happening over here, and again, protecting the iron from oxidation or significant amounts of oxidation, and to keep that storage tank intact. Questions on corrosion? All right, so that's like a combo question of batteries and corrosions together. All right, let's talk about the last thing in this chapter, which is electrolysis. And electrolysis is the process in which we do apply some type of electrical current to cause a non-spontaneous process basically to occur. It is sort of like breaking things apart into their elements in a lot of cases. So for example, if we had some sodium chloride and we pop it in here, we could get out chlorine gas and liquid sodium in this case. And it is a reverse type of process than you may normally think about it. And what I mean by that is in this case, we're actually starting with sodium chloride and we're breaking it apart into sodium and chlorine gas. I'll do a little balancing like I'm in school there. And this is the process of electrolysis when we're breaking it apart. And because of that, when we look at what is our anode and our cathode in an electrolysis cell, it is different than you probably would think. just sort of looking at sodium chloride. So what's happening here in oxidation is it is actually the chlorine going through oxidation. The chlorine on the left-hand side, which is what we're starting with, it has an oxidation state of -1, and it's ending at 0. So once again, in this case, our chlorine is rolling to more positive and going through oxidation. While the sodium here is actually starting at +1 and also ending at 0 over here. So our sodium starting at +1 and ending at 0 is becoming more negative, and it's going through reduction, and it's actually the anode. That is completely opposite of what happens when you make the ionic compound. When you make the ionic compound, you're doing this reaction, and this sodium is going from 0 to +1. It is getting oxidized, and the chlorine is going from 0 to -1, it is getting reduced. So when you make the ionic compound, it is opposite what's your anode and your cathode. This, you can think of it as going backwards in the electrolysis where you're breaking something apart. So instead of a synthesis reaction, you're oftentimes doing a decomposition reaction, which is basically the opposite of a synthesis reaction, and you're breaking it apart. So that's a very common error that people make when they're doing electrolysis cells is they kind of think of it going the wrong direction. They think of it as being made rather than what is happening, breaking it apart using the battery. So you got to think of it sort of the opposite direction. So I'll just put an X through that. So hopefully you won't do that, right? Very commonly as well, we know water. Hopefully you can run an electrical current through water, and you could split water there through electrolysis. Simple 9-volt battery, a couple electrodes, and a little acidic sort of water, and you're good to go. You can split that thing off, and you can produce hydrogen gas and oxygen gas. So once again, here we are going backwards from making water. We're splitting water into hydrogen gas and oxygen gas in this case. Again, I'll do another little balancing there. And once again, if we look what's happening in this direction in the electrolysis, the hydrogen is +1 to 0. So again, becoming more negative. And I'm sorry. Yeah, going from +1 to 0, becoming more negative. So it is getting reduced. The oxygen here is going from -2 to 0. And again, take a look at it here. So +1 for our hydrogen going to 0, so it's getting reduced. And once again here, our oxygen is starting at -2, which would be over here, and ending at 0, becoming more positive in this case. So that is what we see here, oxygen going from -2 to 0, and hydrogen going from +1 to 0 on this side, again being reduced. Now, you usually need the water to be fairly acidic, and that is what we see here with some dilute sulfuric acid. I'll get that name right. We got some sulfuric acid there. What I will tell you, typically speaking, a lot of times if you're reading a problem that is an electrolysis problem, they oftentimes, when it is the electrolysis of water, will not just straight up say, hey, we're doing the electrolysis of water. They'll say something like you're running an electrolysis cell with dilute sulfuric acid or some type of acid. So a lot of times they will not sort of just straight up say electrolysis of water. They'll mention something about an acid, and that's sort of the key. If it's electrolysis, you're probably doing the electrolysis of water, and those would be your half reactions. And that's what we see here on electrical current over. We got the empty spot here in our test tubes. It's not really empty. That's where our hydrogen gas is, right? And our oxygen gas in this particular case. Why do I have more hydrogen than oxygen? The formula is H2O. Yeah, I got more hydrogen than oxygen, right? So you get twice the hydrogen for every oxygen that you're going to get off there. And that's typically what we see. All right, so let's talk a little bit about electrolysis sort of calculations. And there's kind of like very standard sort of beginning to electrolysis calculations. You're either going to kind of go in this direction or backwards is basically most sort of electrolysis sort of problems. So Usually in electrolysis problems, they will give you the current that the cell is run, and that is usually given to you in an amperage, which is again our current. And a relationship between an amperage here and some helpful units is a coulomb is equal to an amperage times a second, which means this is also equal to a coulomb divided by a second. If you divide that to the other side there and solve for A. So that relationship to the amperage there is a coulomb, which is a unit of electrical charge over a second is really important. Oftentimes they will give you the time that you ran the cell for. Now, if you're kind of going in this direction in the calculation, usually your first step is to take the time and convert it to seconds, and then take those seconds and times it by the amperage, which is coulombs per second that you ran it for. And that will give you basically your coulomb of electrical charge here. Once you sort of have that, we will then use our friend Faraday's constant, and we can use Faraday's constant to basically go from coulomb of charge to moles of electrons. So you'll divide by 96,500 coulombs per mole of electrons. You will now have moles of electrons. And at this point, this is where the balanced half reactions come into play for your anode side of your electrolysis cell and your cathode side. In your half reactions, you will have, for example, something like this, where we have electrons to, say, the metal, for example. And you can use stoichiometry basically to figure out how many moles of electrons there are in the half reaction to moles of what you're looking for, maybe the metal or the non-metal. So you can use the half reaction to basically go from moles of electrons to moles of either the metal or the non-metal. Once you have the moles of the metal or non-metal by using that sort of relationship that you get there, you then will convert it perhaps into grams because you have moles of everything. And you can figure out how many grams you would produce in a cell. Obviously, if I have moles and I want grams, I need the molar mass from the periodic table, right, to do that conversion. And that's what we'll use to do that. So for example, here, I could say for every 2 moles of electrons, I would have 1 mole of whatever my M was in that particular case, which again, you can use as a conversion factor. So that's a very common ending to sort of figure out how many grams of something that you would produce if you ran this cell for 5 hours or whatever it may be. Now, not all of the time will our electrolysis always produce maybe like a solid, like we just saw there with sodium chloride, or even with water. Oftentimes, these electrolysis cells will produce gases. And usually, if they produce gases, we get a throwback equation, a little P equals nRT action is sometimes needed to figure out the volume of a gas you would collect. So volume nRT over P in this case. As you hopefully remember, right, if you're using the ideal gas law, our pressure has to be in atmospheres. Our volume is in liters. Our N is moles. Our R is our gas constant, the 0.08206 version. Liters, atmosphere, Kelvin, mole are 0.0821, and our temperatures in Kelvin. So this is also a very common sort of ending for an electrolysis problem is you're asked maybe, how much volume of each gas you produce or how much volume of the gas you would be produced in. They obviously would, in that case, give you a temperature and pressure on the problem as well, so that you could use something like the ideal gas law. Any questions on that? So let's take a look at one here. We'll come back to this one here. We'll do this one. So we want to know in this case how much calcium would be produced in an electrolysis cell where we have molten calcium chloride. and we run it at a current of 0.452 amperage, and we run it for 1.5 hours. So once again, in this case, we have to, when you see this ionic compound, you don't want to think of it in electrolysis cells being made, but again, it's being broken apart. So if you think about sort of the overall situation here, we're going to take this calcium chloride down to calcium, and we're going to make some chlorine gas in this case, maybe not without the two there, but some chlorine gas in this case. So these are our sort of half reactions. It's going to be calcium going from a +2 to calcium with no charge, and it's going to be a chloride going to chlorine gas. So once again, if we look at what is happening in this situation, the calcium is +2, and the calcium with no charge obviously is 0. It is becoming more negative. This is actually our cathode in this reaction, as it's becoming more negative and getting reduced. The chloride is going from -1 to 0, so again, becoming more positive, and this would be our anode in this particular case. That means that this guy would have a couple of electrons going there, and I kind of put the electrons in that side. Oops. Any questions on that there? All right, so since we have our cathode and our anode sort of identified, we can really get into sort of the problem at this point. We are given that this cell is running at 0.452 amperage. Once again, remember that an amperage is a coulomb per second, so that's basically 0.452 coulombs per second. That is important for our time that we're running this thing for, which is 1.5 hours. Again, to make sure everything cancels out correctly, I'm going to turn my hours into seconds. So in 1 hour, there's like 3,600 seconds. That's going to get us 1.5 times 3,600, about 5,400 seconds. And now I really have the makings of my beginning part of the calculation here. I'm going to take my 5,400 seconds, which is how long I ran it for. I'm going to times it by the current there. The seconds here are going to cancel, and that's going to give me basically the coulomb of charge there, which in this case looks like a 2440.8 coulombs. Once again, we want to get this now into moles of electrons, so we are going to use Faraday's constant to do that. And it is a constant, just like we've used in all those other equations. That's our 96,500 coulombs. And this is going to basically be per mole of electrons. So that's going to turn us from our electrical charge into moles of electrons, a little 96,500. Going to get us a 0.0253 moles of electrons. First up, any questions on the calculations so far? Now that I have that, that's really where we can now use our half reactions here to figure out what we want. So in this particular case, we're interested in calcium, so we'll go there first. And we look at the calcium half reaction. For every 1 mole of calcium, I get 2 moles of electrons. So just like kind of stoichiometry, 1 mole of calcium will get me 2 moles of electrons. We're going to use that as a conversion to go to moles of calcium. And we're interested sort of in the solid or molten calcium in this case. And we got 0.0253 moles of electrons. Again, 2 moles of electrons on the bottom gives me 1 mole of calcium. And in this case, we'll do a little dividing by 2. Going to get us a 0.0126 moles of calcium. At this point, we're looking for how many grams of calcium. So we go to periodic table there. And I believe calcium is 4008, I hope, grams per mole. I'm going to go with that and hope for the best. We're going to times it by 4008. And that's going to give us that if we ran this cell, we would produce something like 0.507 grams of calcium in this particular case. Any questions on that there? In this case, they really didn't ask for chlorine, but you could have done chlorine as well. So you could have picked it up, obviously, here, and you could have done the same thing with chlorine, point zero, what's it, 253 moles of electron. You could have went to chlorine and saw as well as a similar sort of conversion. 2 electrons gives us 1 mole of chlorine gas. Which is 0.0126 moles. And once again, if you wanted grams of chlorine, you could use the molar mass of it. If they gave you a pressure and a temperature, you could have figured out the volume of chlorine gas you would produce by using the ideal gas law in this case. Any questions on that? So I would say this is a pretty straightforward electrolysis sort of problem. Variation on this problem would be like maybe they tell you how much you produce and you got to calculate backwards to figure out maybe what the amperage was or how long you ran the cell for. So that's the kind of variation usually on that problem. Any questions on it? All right, let's go back and do the one we skipped here, which is this one. A current of 1.26 amperage is passed through an electrolysis cell that contains sulfuric acid. He ran it for 7.44 hours. Write the half reactions and calculate the volume of each gas at STP. So once again, if you read this problem, there's absolutely no mention of water. And as I mentioned before, it mentions something about sulfuric acid. So this is the electrolysis of water here. So we are again breaking our water up into it. So you don't have to worry about the half reactions. I'll give it to you here. So these are the half reactions that we saw earlier. So why don't you use that? And what we're basically looking for in this case is the volume of oxygen gas and hydrogen gas at STP. STP again is standard temperature and pressure. That means the pressure is 1 atmosphere and the temperature is 273 Kelvin in this case. All right, so take a few moments there and see what you get, and I'll put the other stuff 126 and 74. So we ran it at 1.26 amperage for 7.44 hours. All right, so take time. Ideal gas law may be involved here. Okay, let's take a look since we're getting to the end here, just to finish it out. Again, we basically have how long we ran the cell for and also the current. So we could regularly start this just like we did the other one and basically figure out our coulomb of charge. Again, remember that an amperage here is a coulomb per second. That also means that we do want to kind of get this guy into seconds. So go 7.44 hours and do a little conversion there, an hour is 3,600 seconds. And we'll end up with, looks like 26,784 seconds. We could use both of those together, just like we did in the previous one there, to get our coulomb. So 26,784 seconds times our coulomb per second here, 1.26 coulomb per second. That's going to get us about 33747.84 coulombs. Once again, this is where we use Faraday's constant to go from coulombs to moles of electrons so that we can eventually use our half reactions there to get to moles of what we're interested in. So here we're just going to divide by Faraday's constant. And that's 96,500 coulombs is 1 mole. And again, that is a constant. And I'll just pop the number over here and we will end up with looks like 0.3497 moles of electrons. In this case, we are interested in both oxygen and hydrogen, so we are going to go to both half reactions to get the moles of each of those guys. So let's start with our moles of oxygen. So again, looking at the half reaction for oxygen, we can see for every 1 mole of oxygen, we get 4 moles of electrons. So for every 1 mole of oxygen, 4 moles of electrons. And again, we're going to use that as a conversion factor. So we'll start with our moles of electrons we just calculated. And again, using the balanced half reaction, we will see that we will end up with 1 mole of oxygen on top 4 moles of electrons on the bottom. So we're basically just going to divide that guy by 4, basically. And I'll get a 0.08743 moles of oxygen. We'll do the exact same thing here for the hydrogen since we need both of them. So moles of hydrogen. Now, when we look at hydrogen's half reaction, there's a 4 on the outside and it is in parentheses. So really this 4 gets multiplied to everybody inside. And if we do that for hydrogen, that's going to give us basically 4 moles of electrons. And that's 4 divided by 2, or 4 times a half, will give us 2 moles of hydrogen. That's also a 1 to 2 relationship. If you want to reduce it down any further, you can, or you can leave it as 4 to 2. But that's the relationship we're going to use there. So again, using our moles of electrons and the relationship we got from the equation, I'm just going to use the relationship I wrote there, which is 4 moles of electrons is 2 moles of hydrogen gas. And again, you could do 1 to 2 on that as well, which obviously is the same thing. And that's going to get us, looks like 0.01749 moles of hydrogen. Any questions so far? In this case, we are looking for a volume, and we are given STP, so PV equals nRT is in play. Here we're going to solve for the volume of oxygen, which would be nRT divided by P in this case, and putting in our numbers there for oxygen, 0.08743. The gas constant, 0.08206. Remember, we're not using the one with energy in this case. We've kind of used it a lot. 273, and it's all going to be divided by 1 atmosphere, which is our pressure. And that's going to yield us 0.08743 times 0.8206 times the 273. That's going to get us a 1.96 liters in this case, as that's the only unit left after all these guys cancel, of oxygen. We basically could do the exact same calculation if you chose to for hydrogen. The only difference is going to be we're going to use hydrogen's moles. So hydrogen's moles was 0.01749, 0.08206, 273, which is our STP, and our 1 atmosphere. Again, everything is going to cancel here except for liters. And if we do that, 0.01749 times 0.08206 times 273, gonna get us here. Like I miss a 0 on my calculator. I'll try that again there. 0.08206 times 273. So I miss a 0. My one up there, 0.3497 times 2 divided by 4. I did. I added a 0. That's bad. I was trying not to. I think I added a 0 there. All right. So this is supposed to be up here for the hydrogen, 0.17485. So get rid of that there. 0. There we go. So 0.1749 times 0.08206 times 273. That's going to get us our 3.92 liters of hydrogen in this case. Now, as you also might remember from last semester, when you are at STP, if you did not want to use the ideal gas law, you could use this conversion that 1 mole of any gas will equal 22.414 liters. So if you wanted to, because you happen to be at STP, you could use the correct moles, unlike I did the first time. And you could use that relationship there. Moles will cancel, and you can get yourself there as well. Remember that you can only use that conversion if it is STP. If it's not, you do have to use the ideal gas law if it's not under STP conditions. So this can only be used without STP conditions. Earlier, we talked about twice as much hydrogen than oxygen, and that's what we got here in the calculation, right? So 3.92 liters of hydrogen, 1.96 liters of oxygen. 2-to-1 relationship there. Any questions on that? That is chapter